Good evening, everyone, and a very warm welcome from Open Ideas Lab. Well, at Open Ideas Lab, we believe that curious students like you learn best not by just memorizing textbooks, but by wrestling with the real world challenges alongside real scientists and mentors. Today is one of those rare days when the real scientist part reaches Nobel level. It's my absolute pleasure to welcome our guest of honor, Nobel laureate, Professor David Wineland. Professor Wineland is a pioneering physicist whose experiments have literally changed how we measure time and how we understand the quantum world. He shared the 2012 Nobel Prize in Physics for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. Well, in simple terms, he figured out how to gently hold and control tiny changed charged atoms called ions and listen to what the quantum world is trying to tell us. Using electric fields and laser light, his team trapped single ions, cooled them to nearly motionless, and used them to build some of the most precise clocks ever made. Clocks so accurate that if you had started ticking at the Big Bang over 14 billion years ago, it would be off by about 1 second today. Those same ideas are helping scientists build future quantum computers that can tackle problems ordinary computers would find impossible. Now, that may sound very advanced, but here is a fun part for all of you. Professor Wineland has often said he's not special, just someone who stayed curious, kept asking questions, and enjoyed discovering new effects in nature. Many of his breakthroughs begin the way your projects have begun, with a question, a what if, and the courage to try, fail, and try again. So, if you have ever wondered, can we use light to slow atoms down? Can a single ion be a clock? Or simply, how far can curiosity take me? Today, you can get to ask some of those questions to the person who's actually done it. And I promise you, he's here not to trap students, only ions. Students of Open Ideas Lab, please join me in giving a loud, curious, and very enthusiastic welcome to Nobel laureate Professor David Wineland. Over to you, Professor. Thank you.
Yeah, Professor. So I've got the slides with me. We are on the first slide, the summary slide, atomic
Okay.
clocks and Einstein's relativity.
Okay, so I can go ahead then?
Yes,
Yes.
please.
Okay.
Go ahead, Professor.
So,
Yeah.
okay, just to summarize out, I'm going to give you a little bit of my personal history and background, and then I'll go into why do we need precise clocks? And the main reason is that for centuries they've been used in navigation. I'll talk a little bit about that. I'll give some idea about how the basics of atomic clocks, and these days our atomic clocks that run at optical frequencies, and I'll say a little bit about that using some examples from the lab I was at previously at National Institute of Standards and Technology in Boulder, Colorado. And I'll finish with giving roughly an idea where things are at right now and where we're going in the future. So in the next slide, I have a little bit about my personal history. So my parents were products, you'd say, of the Great Depression. That is, they lived through the Great Depression in the U.S., which was basically from around 1930 to 1940. And so during that time, a lot of people in the U.S. didn't have jobs, so it was a big problem. And so my parents were fortunate to have jobs, and anyway, but during when my sister and I were growing up, they certainly emphasized the importance of getting a college education. And with them, it was mainly to find a good job. But of course, having a college education is, allows you to do many things. So anyway, with that, with their emphasis in mind, throughout school, I tried to get good grades in my classes, but my parents gave me a lot of freedom to explore. So if you can see the pictures here, when in the mid 50s, I was interested in model airplanes, and then I actually got my first car when I was 14. I couldn't drive it yet because the driving age was 16, but I bought the car, and for almost a year and a half, 2 years, it needed a lot of work. So if you can see on the right there, the car was a 1932 Chevrolet, and as I say, it needed a lot of work. So I had to go through that, and which is a good experience. I learned a lot about mechanics, and oh boy, I'm sorry, I'm having trouble with my slides on the side here now. Uh, anyway, so anyway, my friends and I were all interested in cars, and so we in the lower left there you see my friends and I working on a 1936 Ford, modifying it, and in fact we had a little business going. We would buy these older cars and fix them up and then resell them. Uh, so we had a small business going. Anyway, along that time, at that time, though, I was in high school, and I took my first class, and what physics class rather, and what I liked was uh, with relatively simple mathematics, you could explain much of the phenomenon you see around us, and so in the next slide, I next slide I show. Let me get my screen fixed here. Sorry. Well, I show. I should give a brief explanation of navigation, and uh, so historically, the way sailors would navigate on the seas, that for example they could find their where they were in terms of latitude by basically on the northern hemisphere, the main method was to look at the focusing on the North Star, and if you then measured the angle theta, as I show here, basically that uniquely determines where you are north-south. That is in terms of latitude on the Earth, and then the idea after that is that uh, for longitude, the east-west, the same principle applies, but also in order to interpret what the angle was telling us in terms of longitude, we had to know the time. And so just to give a little bit of history, and so in 1714, the British Parliament, after a number of naval disasters where they lost ships due to the fact that people couldn't navigate, they 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 sponsored a prize, 20,000 pounds, to provide a clock that could give accuracy of 30 nautical miles in terms of longitude, and that corresponds in terms of this angle here, that corresponds to that precision corresponds to a time accuracy of about 2 minutes, 120 seconds. And anyway, so there was a clockmaker, John Harrison, who took this challenge up, and he was actually able to make a clock that would satisfy this condition. And I mentioned at the bottom right here, if there's a not nice non-technical book that I like that you might check about the history of John Harrison and his clocks. In any case, that was that was one of the first important applications of clocks, and of course the precision wasn't very high, but nevertheless, got this thing started. So on the next slide, I talk about modern navigation via satellites, and there the ideas were if we have if we have a clock on Earth and it's synchronized with a clock on board a satellite, then we can measure it. That is, if we're always on the same second precisely, then by some protocol, the satellite will emit a pulse of radiation, and it'll be delayed by the time the speed of light given over this distance. But from that, we can determine our distance from that satellite, and the air there, what I'm writing is delta L, is basically the speed of light times the uncertainty in the time. So for uncertainty in the clocks, in their synchronization of about a nanosecond, that gives a precision of about 30 centimeters distance. And of course, there's a network of satellites, so we can get our position in 3 dimensions. And so basically, so we needed this. This is where the things are today. We can get a precision in our timing of about a nanosecond, which gives, uncertainty in position of about 30 centimeters, which is just fine for normal navigation, of course. So anyway, so this precision of 30 centimeters is basically, if we turn that into an imprecision of time, so it's about that 1 nanosecond divided by 1 day is about part in 10 to the 14th. So our clocks need to be synchronized with that level of precision. So in the next view graph, I show you the system in 3 dimensions, and so what's called the global positioning system it has a network of satellites, and so we can determine our position in 3 dimensions, and of course it's more than 4 satellites, so there's a lot of redundancy and to refine the precision. But that's basically how the modern global positioning system works, and so we need a minimum of 4 satellites to give both the space and to give the time synchronization. So in the next view graph, I labeled clocks. Basically clocks are based on, we have some on the left side there, we have some periodic event generator and then a counter, and that basically gives us the time. And so frequency references, traditionally one reference is of course the rotation of the Earth, but for many years, for more than a couple of centuries, the most accurate clocks were pendulum clocks, based on just the oscillation period of a pendulum, which you see on the right-hand side of the view graph. And so basically the atomic oscillations act like a pendulum clock. And so what I've shown on this picture is it shows on the upper right-hand side, and I'm not sure if the animation is working for you, but basically you see the density for a single electron in an atom, in this case in a so-called p orbital, the electron is oscillating back and forth basically through the nucleus, and its position is given by the density of the picture you see. So it's oscillating in this case vertically in the picture. And that one thing to point out here is that the electron in an atom is not, the reason it's smeared out is that the electron is actually smeared out due to the limitations of quantum mechanics, but nevertheless we can see this precise oscillation of the electron density oscillating back and forth, so-called electric dipole transition. So one thing is that one clocks these days are, well, starting decades ago they were first on masers or lasers, and people I think are familiar with lasers. That stands for light amplification by stimulated emission of radiation. And masers is the M just is stands for microwave rather than light amplification, as for lasers. But the idea is exactly the same. So the in the lower right hand part of the slide, basically we have atoms inside of a cavity. So particularly for lasers, this is the way a laser works. It will have a sample of atoms in between two mirrors, and the atoms are continually fed into this cavity, and when they emit radiation, and it's determined in part by the cavity. There's a resonant frequency of the cavity, but anyway, when that's tuned in sync with the atomic frequency, then we measure the oscillations coming out of the radiation coming out. And let's see here. Sorry, that part didn't work very well. Sorry. Anyway, so that's the basic idea. Is we need to measure this radiation, and if we choose a particular atom, that gives us a standard for this radiation period. So in the next group, in the next slide, I show the picture of Norman Ramsey's group at Harvard University. So I had gone to I had got my undergraduate degree at the University of California, Berkeley, and then after I got my undergraduate degree, I went to Harvard, and I worked under Norman Ramsey, and Norman Ramsey was probably one of the most famous atomic physicists during the middle part of the last of the century, and anyway, he was very well known, and you could see if you have the view graph, you can see the group is fairly large, and I put a little sign there, where are the women? And I think it's, obviously there weren't any women in this picture. To give you an idea that for whatever reason, and I think it had to do that in the basically women were discouraged from going into science, and it's just some bias that men had, I think, unfortunately. So you can see in this picture there weren't any girls in our group, but that wasn't due to any prejudice, for example, from my advisor Norman Ramsey. It was just that was the way things. Girls just weren't encouraged to go into science. Anyway, so my thesis was to build a maser based on atomic deuterium. Norman Ramsey and his colleague Daniel Kleppner, who then had gone and took a position at MIT, they had invented and demonstrated the first hydrogen maser. And basically the idea there is that hydrogen has there's a so-called hyperfine frequency, and it's based on a transition between the two energy levels where the electron spin in hydrogen is either parallel or anti-parallel to the nuclear spin. And that energy difference between those two configurations corresponds to a frequency of about 1420 megahertz. Well, the idea is the same. In my project, was based on atomic deuterium, and deuterium, of course, is just an isotope of hydrogen. So the main difference was the the nucleus has a different magnetic moment. So the frequency of the so-called hyperfine transition in deuterium is about 327 megahertz. But anyway, my task in my experiment was to measure it precisely, and that's the number you see on the screen there. And the basic, emphasizing all the way through in clocks, to get these precise values of the frequency, we needed precise control of the environment. In case of hydrogen and deuterium, we needed the external, the applied magnetic field very, very precisely, so that and other controls of the environment. In particular, we had to get rid of other atoms that might contaminate the system. I haven't described the masers really at all, but basically the hydrogen maser and the deuterium maser, the same principle. They work on atoms and in case of both hydrogen and deuterium, they were stored in a quartz bulb inside a resonance cavity, and to prevent the oscillations being diminished by colliding with the walls. Actually, the trick was to coat the inner surface of this glass. It was a quartz bulb with Teflon, and that worked pretty well so the atoms could collide with the wall without killing their oscillations. So anyway, that was the main feature between the hydrogen and deuterium maser. And actually, the Norman's group also later measured the tritium frequency, which is the third isotopes of hydrogen. But the one that was kept the most in use was the one based on atomic hydrogen. So in the next view graph, I have just a picture of kind of give you a rough idea. So of how things work. Now, what I'm showing here is actually a transition, not the hyperfine transition, but this would be an optical transition, for example. And for an optical transition, we can think of this superposition of two energy levels as an oscillating electron density and basically an electric dipole. Even though the electron is smeared out due to quantum mechanics, it still oscillates, and it's that oscillating electron density which gives rise to the clock. And so it's based on two different energy levels. In the upper left part of the figure, you see the frequency is governed by the difference of energy of two energy levels divided by Planck's constant. And so this is the basic idea of clocks, both based on masers, microwave amplification by stimulator emission, and also lasers. And so basically the idea is we measure the frequency of emission on those transitions, and we would count cycles of the radiation to generate time. And on the lower right, I show we build up this amplitude of this oscillation by having the atoms inside of a cavity, in this case, a microwave cavity. Anyway, the one thing we have to be careful with is that the atoms in the cavity, they're both oscillators, but they're coupled together. And one issue we had with both the hydrogen and the deuterium maser is the frequency of the cavity is not equal to the frequency of the atoms. The frequency that's emitted out of, say, a partially mirrored, in this case, a laser partially coated mirror, the frequency is not equal to the frequency of either the atoms or the cavity, somewhere in between. So we had to compensate for that. And I won't go into the details of how that was done in the case of lasers and masers. It's fairly straightforward, but it's a bit complicated. But another approach is to get rid of the cavity. And so in the next view graph, a more common mode of operation, particularly at microwave frequencies, that we will have the atoms inside this storage bulb, we said, and we'd initialize the atoms in the lower energy state, and then we'd apply radiation for a certain amount of time, and then after that time, we measure the probability of the atom being excited to the upper energy level, labeled 2 here. So and the idea is that when the maximum transition probability is given when the applied radiation frequency is given by the difference in energy levels of the two levels divided by Planck's constant. And so this is our standard. And of course, then if we can satisfy that condition, that is find the maximum transition probability, then we would just count cycles of the oscillator to give us time. So that's the basic time. And of course, for high precision in the lower right hand part of that figure, I show sort of the absorption profile of an atom. In our case, it was deuterium in my thesis. But basically, the atoms don't absorb precisely at one frequency. It's smeared out by, there's a range of absorption, and we want to be sitting right at the top of that absorption peak. And but the range of absorption then is given by 1 over the lifetime of the atom in the excited state. So we wanted very long lifetimes, tau to be very large, and that gives us very high precisions. So in the next view graph, so let's say what's so good about atomic clocks? And so I have 2 columns there that on the left we're going to compare to a pendulum clock, and so on the upper left I show a graphic of a pendulum clock, and basically one of the things we have to worry about in a pendulum clock is temperature. Actually, we do in the hydrogen in the case of lasers too, but I'll explain that in a second. But for a pendulum clock, actually the pendulum clocks are very good, but one problem is that they have if the length of the pendulum changes, for example, typically if temperature goes higher, then the length of the pendulum increases a little bit, and that slows the clock down. So I've written out an expression there where basically that alpha parameter that I write there is basically gives an idea of how the clock frequency changes per degree centigrade, about a part in 10 to the 8 per degree C. For most, even very low expansion, metal thermal expansion coefficient is about 100 times larger than this. So the typical pendulum bobs in a high precision pendulum clock are made out of some ceramic that has a low temperature coefficient of temperature expansion. And anyway, so that's one issue with the pendulum clocks. And on the left there, the reproducibility then depends on the manufacturing tolerances, the length of the pendulum, and also the local value of the gravity. And of course, the pendulum, the pivot point can wear, and so the pendulum gets slightly longer, and that changes the frequency. The nice thing about on the right-hand side, talking about atoms, is that basically, the frequency of the atoms is God-given, and but one thing actually, what Einstein taught us about was that if the atoms are moving, then time moves slower for them than it does for us in the lab. And I write an expression there that if the atoms are moving, basically, that it gives a frequency uncertainty of about 1.4 parts in 10 to the 13 times the temperature divided by the mass of the particles, and that's just given by the thermal properties of a gas of atoms. And so, to give an idea for cesium, the frequency is about the uncertainty in the frequency for cesium atoms is about a part in 10 to the 15th per degree C. So if we can control to a degree C, we have a very precise standard. And so anyway, that's certainly one of the main issues we had to worry about, this so-called relativistic time dilation due to the movement of the atoms. And in the lower right hand there, I just mentioned that. So the nice thing is that all atoms of a particular kind, in the case of cesium, for example, they're all exactly identical. And also atoms don't wear out. There's nothing to wear out in the atoms as long as we can keep them around, which gives the reason they're such good absolute standards. And I showed on the lower right, so for cesium atoms, the frequency, this so-called hyperfine frequency, the same kind of transition that we think about in the hydrogen maser, that was at about 9 gigahertz, as you see in the lower right hand. And in fact, that we could in the early 60s, by the early 60s, we were able to control the oscillation period of the cesium atoms due to very systematic effects and to high precision. So in 1967, there basically the oscillations of the electron in the cesium atom at about 9 gigahertz on the screen, as you see on the screen there. That became the definition of the second. So it was based on this oscillations of the cesium hyperfine transistor. And actually, interesting today, we have much better standards. I'll say a little bit more about, but basically the definition is still based on the oscillations of the cesium hyperfine transistor that I show in the lower right-hand part of that slide. So, and then on the next slide, I start talking about atomic ion traps, and there the two main developers of the ion traps was Hans Dehmelt at the University of Washington and Wolfgang Paul at Bonn University in Germany. And I won't say a lot about that, but for ion traps, charged atoms, I show an electrode structure, and if we apply an oscillating potential between the two N pieces there and the ring electrode, so the N pieces are tied together, and so there's a voltage applied between the two N pieces and the so-called ring electrode. Then on average, this creates a 3D harmonic well. There's a bit of math to go through, but basically you could just assume when we do this, we make a three-dimensional harmonic well, and the atom, a trapped ion in this case, is then captured in the middle of this ring electrode. And so an analogy of this trap, I just say, in 2 dimensions, it's just like a marble in a bowl. The atom can roll back and forth in this atomic trap, but the main thing is, of course, it confines the ion in the trap, so we can hold it for a long time and measure the frequency of the hyperfine transition, for example, more precisely. So, we made clocks with both with hydrogen and deuterium, as I mentioned, but there's other made as well. Even though the definition was still based on this microwave transition in cesium at around 9 gigahertz or so, it was obvious that we could do much better in principle if we used a much faster tick rate that is a much higher frequency of the electron oscillation. And so basically that led us and other people to look at optical transitions. And just to give you an idea, one of the by that time I'd moved to the to the National Institute of Standards and Technology in Boulder, Colorado, and we focused on using a singly charged mercury ion, and basically the frequency I show there is about 1 times roughly 10 to the 15th oscillations per second, but we could measure it very precisely, and so that became another way to make a precise clock. And so in this idea of using an optical transition, you can ask, was that really a new idea? Actually, I include a portion of text from a book that Lord Kelvin William Thomson had made, and his colleague Peter Tate, and they basically just saying, indicate that the pieces of matter such as hydrogen and sodium, they basically in very large numbers, they can provide time due to their oscillation. And so this is basically the idea of an optical clock. So the basic idea goes way back to in 1879, their idea about the oscillations of an electron in a sodium atom, for example, could make a precise time standard. So in the next view graph, I talk a little bit about the work that we worked on using mercury ions. The same idea. It was an outer electron that oscillated at, in this case, an ultraviolet frequency, about a little bit over 10 to the 15 cycles per second. And so one of the issues was, of course, can we tell that the atom has absorbed the radiation? So, for example, I show in the lower part of the picture the purple arrow is meant to represent a laser beam that's at the frequency near the clock transition between these two particular states in mercury ion, and the wavelength was about 280 nanometers. In any case, that was then provided the reference frequency reference, this oscillation corresponding to 282 nanometer radiation. And then we could measure the frequency most precisely if we just put a single mercury ion in the trap. And so even though it took us a while to measure the frequency, we could get the highest precision by just having a single ion in the trap. The problem being with many ions, they collide together in the trap, and that can cause a frequency shift. So the most precise frequencies could be derived by using a single ion in this ion trap. So let's see. So the next picture I shows how do we detect it? Well, in principle, we could look at, as we transfer this with the radiation through let me back up. Well, I won't back up. But anyway, the basic thing is that for a clock transition, it would cause some absorption of the laser beam that was at the clock frequency, but that was very hard to tell the absorption from that. So another detection method, what we use is we'd use sort of indirect detection. And the idea in this graph, where I labeled detection, is what is basically, so our clock transition is from the S to the D level in this picture here. And the way we could tell an atom was atoms absorb the radiation from this laser beam was we'd start the atom in the S state, and then we'd apply the radiation, this roughly 100, pardon me, in this case, the S to D light, which was at 282 nanometers. But the basic idea is we'd start the atom in the ground S state, and then we'd apply the frequency of the clock radiation, S to D radiation. And then if the atom absorbed that radiation, then when we turned on this auxiliary laser, if the atom hadn't absorbed the radiation, we'd see that the atom would scatter light. But if the atom was promoted to this D level, then when we applied this laser at 194 nanometers, the scattering would stop. So we could tell with 100% efficiency then whether the atom remained in the S state or the upper state of the clock transition, the D state. So this is a very nice way to get. We could actually measure with 100% probability where in precision if the atom had made the transition. So this technique is very commonly used in many experiments, and this was how we used it in this example for the clocks. Okay, so in the next part of the view graph, one of the things I show here is that where I have a picture of a single atom that we can, I was kind of, we can actually see a single atom. Well, this radiation is in the ultraviolet, so we can't see it with our eyes, but we can have a sensitive video camera, and I show in the lower right-hand picture there. We can make a picture of the atom with an ultraviolet, sensitive camera, and I show an image of the atom, and you see a lot of scattered light from the electrodes, but the dot in the center of that picture is our single ion. So we can actually very sensitively tell when we have a single ion or multiple ions in the trap this way. And of course, it was ideal. 100% detection efficiency would tell us where the atom had made the transition from the S state to the D state, where the radiation was pardon me, the absorption was stopped. So one of the things we have to worry about is the so-called the Einstein relativistic time dilation. That is for atoms or ions in this case moving, and they experience Einstein's relativistic time dilation. That is, time in their reference frame is moving slower than it is for us in the lab. And we had to, for very high precisions, we had to measure this temperature. And in fact, one of the main things our lab developed, along with other labs, is that we can cool the motion, basically the temperature of the ions, using radiation pressure. And the simple idea there is if we think about the atom and this cooling laser beam, when the atom moves in a direction against the laser beam, that causes the frequency of the laser to be tuned up. When it moves away from that source of radiation, the frequency is tuned down, and it's that difference in the apparent radiation frequency due to this motion is what gives a differential effect that we can measure. And so anyway, we could basically use this radiation pressure where there was a difference in where the atom absorbed radiation, where scattered light, whether it was moving against the laser beam versus when it was moving away from the laser beam. We could actually cool the atoms down. And for the case of mercury, we could cool down from room temperature, about around 300 Kelvin, to about 1 millikelvin, which then would suppress this effect, this time dilation effect by a part in a million. And actually, one of the things our lab, and this was when I had moved to Boulder, Colorado, National Institute of Standards and Technology, and one of our claims to fame was we were the first to demonstrate this idea of laser cooling, which is now common in many experiments. So anyway, in the next view graph, I show that our group as it was in 1979, around the time these first experiments were done. And I show my colleagues there, and this was the size of our group in 1979, and in the mid-90s, it had grown to about 30 people. So we had a number of different experiments going, some, not all of them, based on clocks, but certainly most of the effort was to make precise clocks. So anyway, those are my colleagues in the late 70s. And just to summarize, the person that was mainly the main person involved in demonstrating this mercury ion clock was Jim Berquist, and he's someone basically we spent almost our whole careers together. And anyway, so based on this mercury ion clock, we could demonstrate this very accurate clock. And in fact, I won't go through all the detail. Just briefly mention that, of course, the trapping, first of all, on average, gets rid of the so-called first-order Doppler shift due to the average velocity going to zero. And then by laser cooling, we could suppress this relativistic time dilation. And then, we also trap the ions in very high vacuum, so we get rid of perturbations due to collisions, and also we put the the apparatus, or at least the trap apparatus, in a helium bath, which would significantly reduce black body radiation shifts and systematic uncertainty. So basically, in around 2006, we were able to demonstrate that we could get an uncertainty, relative uncertainty, which was better than the best cesium clocks. And so these days, cesium is still the reference, in partly because for most purposes, cesium accuracy is just fine for most applications. And we do think about, converting to some other standard. Certainly mercury would be a possibility, but there's a number of atoms and ions and their transition frequencies that are better than cesium. So we don't want to just change the definition and maybe some other clock will be better in the next year. So we don't want to change the definition of the second. So it's still, these days, it's still reference to cesium, which is still, even though the accuracy is not as good as with our ions and other atoms, we can still, for most practical purposes, cesium definition of the frequency in terms of cesium is still the way that it's the definition. So if I move to the next slide here, anyway, this shows more recent experiments that we did in Boulder, and this I show my three colleagues, Till Rosenblatt, David Librant, and David Hume, in this next picture. And so in that case, we were using aluminum as a frequency reference, and so one of the advantages was the wavelength is 167 nanometers, so even higher frequency. And the nice thing too is the clock transition that was based on what I show in the picture as the down arrow state and the up arrow state of aluminum. And the way we could tell when we made a transition from the lower clock state to the upper clock state, that is the 3p0 state, is that after we shine the radiation for clock radiation frequency, if the atom had made the transition, then we'd turn another laser on that I show is 167 nanometers. And if the atom had not made the transition, then when we turned on this 167 nanometer light, we would scatter radiation, and we could tell immediately that the atom was in the ground state. But then when we made the transition to the 3p0 state, then when we turned on that second laser, there would be no scattering. And essentially, we could get 100% accuracy on whether the atom had made the transition. So there was a lot of things to go through this, and over the years, we had another colleague joined us, James Chow, and anyway, and just to give it, one of the landmarks is that we could, in experiment led by James Chow, is that in 2010 we could reach a systematic uncertainty based on all the environmental effects, which is slightly less than a part in 10 to the 18. And this is still, this is one of the best clocks still. But as I say, we still haven't, the definition haven't changed because there's a number of other transitions in atoms, in neutral atoms, and in other ions that we play with. So in the next view graph, I give a little bit more of a picture of the aluminum clock. It shows the apparatus, and you can see in this picture on this view graph that we see a optical table in the background, and our ion trap is a tiny part of the apparatus. You see on the table, basically our trap, you can't see it in this figure, but it's right where the arrow is pointing there. And so that's where we had our single ion to make this aluminum clock. and the upper lifetime there is about 20 seconds. So the relative precision, it has extremely narrow line width at this very high frequency. But the main thing is that we could actually show that the uncertainty due to all the important systematic effects due to collisions, black body radiation. So we could get the systematic uncertainty to just below a part to the 10 to the 18, and that's the reference I quote on the bottom of that slide. And this was by this time it was mainly work due to David Librand and David Hume in our lab. So in the next view graph, I go through some of the effects summarizing some of the effects we have to correct for. So obviously we need to worry about electric and magnetic fields, and there's certainly relativity, and we have to worry about the shifts of the frequency due to the movement of the ions. And by laser cooling, then we could suppress those sufficiently. But and that's what I'm calling this time dilation due to atomic motion. That's the relativistic shift I talked about. But we also had to, we had to consider that, that there's a gravitational potential shift due to our clock atoms, in this case being aluminum, which is about this frequency shift, gravitational potential redshift, is actually very large. It's almost a part in 10 to the 8th, and so we have to measure the transition very precisely. And also this says that also if we want to compare two clocks, they basically have to be basically in the same place in the same lab, otherwise they'll see different gravitational potential redshifts. Anyway, to give a graphic example of, I pose a little story down at the bottom of this view graph, which is, suppose you and your twin brother or sister were separated at birth, and you live at sea level, and your twin lives in Boulder, Colorado, which is about 1.6 kilometers above sea level. And after 80 years, your twin will only be about a millisecond older than you. So in our daily lives, it doesn't measure. But for the precise clocks used for navigation, we need to take care of this gravitational potential redshift. So anyway, just to mimic, the gravitational potential redshift or to show it on a human scale, I shown this picture. Here's the two guys that developed the aluminum clock, and in the background you see our apparatus for aluminum clock on this optical table, but we also, for comparison, we had an adjacent lab just adjacent to this. The lab where this setup was, we called that clock number one, and in the adjacent room we had another clock, and we could measure the frequency of the two transitions to about a part in this case. We could actually do better than this, but it was about a part in 10 to the 17 in this at the time this picture was taken. So basically unfortunately this picture won't look very good, but basically what we did is just to compare, we in our main clock, what I was showing in this picture, James Chow put some jacks underneath the optical table, and in a sequence of photographs, he lifts up the table that has our one aluminum clock on it, and the animation was better. But basically, we raised the clock, the table that this aluminum clock was on, by about a foot or so, and we could, anyway, when we could actually measure this effect of the gravitational potential redshift, and you can see it's an extremely small effect. It's lower than a part in 10 to the 15, but with our very precise clocks, we could tell that time was running different for for this aluminum clock when it was sitting on its legs versus when it was raised up about a foot, and we could measure that difference in time. Okay, so let me just see what get that. So anyway, just to give you an idea, we're at this level of about a part in 10 to the 18 uncertainty, and there's many other experiments being done. I showed that, our experiments based on aluminum, singly charged aluminum ions. One of our colleagues just down the street from us at the University of Colorado, the Joint Institute of Laboratory Astrophysics, is Jun Yi, who's done a lot of nice experiments. He's in the experiments I show here. He did similar clock experiments on neutral strontium ions, and basically this cartoon is meant to present this kind of pancake structure. Is basically it was a standing wave at another, not the clock frequency, but a frequency that could hold the atoms, and so he was able to make pancakes of his strontium atoms, and he could they were separated by about 400 nanometers with these pancakes, and he could measure the difference between the time on two clocks, basically separated by just 400 nanometers, and he's continuing with that group. Actually, I don't have time to go through. This was based on an optical transition in the strontium atoms, but now he's also measuring the time dilation on nuclear transitions inside of trapped atoms. Okay, so anyway, we could think about these clocks based on nuclear transitions, and one example that this group at UCLA and also Chun Yi are measuring is basically based on thorium nuclei in a solid host. And anyway, the precisions are very high, and we use similar methods that we use for atomic ions. But anyway, we'd be able to improve the precision. Actually, one of the other things that's another whole topic in itself is we could measure what we call spin squeeze states, and as I say, this is another whole topic. But basically, we can squeeze the uncertainty and the velocity of the atoms using these so-called entangled states. As I say, it's another whole lecture to give you an idea what's going on. But the improvements continue with these various methods. And so another, just as an example, one of the example for these might be used for these very precise clocks is, for example, we can measure the Earth strain. And so basically the idea is if we have two of these very accurate clocks separated by, maybe just a kilometer, we can, through the gravitational potential redshift, we can see that their relative heights compared to the center of the Earth are changing. And one reason that's interesting is that this strain is basically that in an earthquake, basically the positions of, in this case, the two clocks, their height is changing, over slow, slow times, but basically when that's indicating a strain. This change in height indicates strain in and basically when eventually this strain lets go, which gives rise to which gives rise to the earthquake. And the idea, but anyway, is that maybe we could use these very precise clocks to measure the strain before an earthquake and be able to make predictions about earthquakes. And of course, there's, in the last bit I show here is there's very fundamental sciences and fundamental experiments we're thinking of. And one thing, by comparing, these different accurate clock frequencies for different elements, if basically, if we can rule out all the environmental and systematic effects, the changes of these relative frequencies due to the different basic forces show that the strengths of these forces, these fundamental forces, are changing in time. And of course, we can use these to detect gravity waves, and also, one of the in the end, we all these relativistic shifts that come from Einstein, and so maybe will we be able to see deviations from Einstein's theory of relativity. So far, he's in good shape. We haven't, we can measure the shifts that he predicts, but we haven't found any deviations. So anyway, this gives an idea of where the technology is maybe going. Maybe we can see deviations from Einstein's theory, which signify new physics and so on. And anyway, just for an example, for example, I talked about the relativistic Doppler shift from due to clocks on Earth, but one just for fun, another source of gravitation is the Virgo galaxy clock cluster, which has millions of planets in it, and anyway, this Virgo cluster has a mass of about 10 to the 15 times more than that of the sun, but it's separated by a large distance. But we could see we can, if we had some way to move the Virgo cluster around, then we could see the shift, because it's actually about 5,000 times larger than the shift due to the gravitational field from the Earth. And the one thing to say is basically this, the relative distance isn't changing over any human time scale enough to matter. So basically, that shift is the same almost anywhere on the surface of the Earth. And so it's more just illustrative of the kind of precisions we could get. And I just want to say that, this shows our group. I was at NIST until 2018, and for reasons that didn't have anything to do with physics, I moved to the University of Oregon, where I am now. But basically, at the time, just before the time I was leaving, this shows the group at NIST, the clock group. You can see it's a lot of people. And the other thing to say is there's a lot of people working on various experiments. And the other thing to say is we had one of the nice things for our group is we had very great leaders. And so one of the leaders was Catherine Gebbe, who was the director of the lab, and she was not only helped us with funding, but she was very important to be able to form this group. So due to her foresight and direction, we were able to accomplish some very nice experiments. And I just say just a couple of words about the work at Oregon. And at Oregon, this shows our group. This is actually a couple of years old now, but it shows our group. It's formed by myself and David Alcock, a former postdoc in Boulder. And anyway, this shows the group from a couple of years ago. And basically, what we're trying to do there is study, transitions in this case, calcium-40 ions, and these can be used as frequency references in various experiments. I don't have time to go through all the different applications there, but our group has grown through the year, and just give an idea of some recent topics is that we can measure scattering out of metastable atomic states. We can talk about in the third bullet there two-mode squeezing. That is, we can squeeze the extent of motion of our ions in the trap. And anyway, I won't go through all the different experiments, but anyway, but thanks for listening. And I with that, I'm returning to it. I'll stop there and just thank you for listening, and be happy to answer any questions you have. Thanks.
Trey, I think that's all we have with the questions, I guess, unless I missed out someone.
I think we have covered everybody. Thank you everybody for joining in. Really appreciate your time. I know it's late evening for at a lot of places, so thank you, Professor. Thank you. I know it's been like the last couple of months we have been actively speaking. Thank you for all the efforts and all the work and this
No,
great presentation.
I was happy to do it. And for all the students out there, I wish you good luck in your careers. And anyway, I think there's lots of new things to discover. So I wish you luck with that.
Thank you so much, Professor, for your taking the time out early in the morning on a Friday. I know that's tough in San Francisco in a spring morning. So wish you a great weekend.
Okay, well, thank you. Anyway,
Thank you.
thanks very much.
Thank you.
All right. Bye-bye.